Okay,
Looks
so
like
it's live. All right, I'm going to share my whole screen, and we can get going. All right, does this look right? Can everyone see it?
yes.
Cool.
Not anymore. Yes.
Hit present to everyone. I don't know whether that makes a difference. Okay, all right, so let's get going. Other people might join as we go, but yeah, that's them. So yeah, as I said a moment ago, the aim of this call is really to discuss how we can integrate existing algorithms into NILMTK. We're first going to talk about the interface to disaggregation algorithms that we've already specified in NILMTK, and then we'll talk about two other algorithms, one by Mingjun and one by Stephen, and we'll talk about how the algorithms work at the moment, but also whether the NILMTK interface is sufficient for these algorithms and how much work it might be to adapt them to use the NILMTK disaggregation interface. And then we'll end up with a bit of Q&A at the end. But so just seeing that Jack said he has to go at 5:30, I pretty much have to go at 5:30. So let's try and squeeze this all into 1 hour, with roughly 15 minutes for each. And we have time at the end for some off-topic conversation, but we'll try and cover these first three elements as quickly as possible. But we want to have good discussion on each of the points. Does that make sense to everyone? Is there any questions before we get going?
I'm okay.
I'm fine. Yeah. I'm okay. Yeah.
Sorry, did you just say something, Mingjun?
No, I said I'm okay. It's fine. Yeah.
Ah, you're okay. Cool. I think it dropped, or I didn't receive your audio anyway. Then. Cool. Okay, let's get going. So I'm just going to talk through, I guess, to start with the disaggregation interface for NILMTK at the moment. So can you all see the code that's on my screen at the moment?
Yeah. Yes, I can see it. Yeah.
Cool. So this is the disaggregator superclass, if you like, and I don't know. I think Jack tells me this is not very Pythonic to have an interface specified without any code in it, but this is the only way I knew to kind of specify the methods which we want disaggregator subclasses to implement.
It's fine.
And the aim is to have some consistency across each of our disaggregation algorithms. So we have a few benchmark disaggregation algorithms in there at the moment, but hopefully Stephen and Mingjun, if your algorithms could use the same interface, whatever that may be, then that's kind of the aim. So the disaggregator interface is kind of built around 6 methods. So there are 2 training methods, these 2 at the top here. Really, train is the one that's exposed publicly, I guess, and train on chunk comes from the internal chunking in NILMTK. And the logic behind this is that we want to still support data sets that are too large to fit into memory in NILMTK. So we have this chunking, which means that we only load a single chunk from this whole data set into memory. We do some processing on it, and then we write the output back to disk. And this kind of looping over chunks allows us to run our algorithms and analyses over data sets that are too large to fit into memory. So this whole training stuff, you call train, it's going to take some NILMTK meter group objects, and ultimately it's going to store. Well, it's going to store whatever it's learned in memory. So it's at this stage it hasn't written anything to disk. So that's how training works. So train would really loop through the chunks and call train on chunk for each chunk, and you'd end up not returning anything from these methods, but just storing the learned model in memory. Okay, that's how training works. I'm going to skip over disaggregation here and go down to importing and exporting the model. Now, I think both Stephen and Mingjun have come across this exact problem in that training often takes a long time, and it's not something you want to repeat every time you kind of restart your Python environment. So it's really nice to be able to save your model to disk and then to be able to load it from disk again later.
Yeah,
so,
I've actually on mine I have import and export functionality, so this would work. Yeah,
so I mean I don't think we specified this originally, but it makes a lot of sense practically, especially if you want to train once and disaggregate lots of other things. So I think this is good, and we tried to unify the interface here. So export will take the model in memory, save it to disk, and then import will do the opposite. It'll trash whatever's currently in memory, and then load the model from disk and store that in memory. So relatively simple. Again, they don't return anything. They're just either memory to disk or disk to memory. Then the last two sets of methods are the disaggregation methods. So these are kind of like the training methods in that disaggregate is really kind of the main public method that you'd call with some mains data, which you want to disaggregate. It's like the input to the algorithm, and an output data store. And this is kind of important because, again, the disaggregate function doesn't return anything. Rather, it writes the output to disk into this output data store. So really what disaggregate will probably do internally is it will probably loop over the chunks in the mains data and call disaggregate chunk on each of those chunks. I think disaggregate chunk is, I guess, a special method in this class because it's the only one that actually returns something. And this will return a pandas data frame where the columns are the disaggregated appliances and the rows are kind of time instance at the same time instance that were passed in the mains method. So really, disaggregate chunk will perform all the hard work, do the disaggregation, and return a data frame representing the disaggregated chunk to the disaggregate method, and then the disaggregate method will take care of writing that to disk. There's one other method, this write disaggregated chunks data store. We never implemented this, and I don't really think it makes sense to use this method anymore. It turns out that actually writing the chunk to disk is a one-liner anyway, so I don't know if it makes sense to have a whole method dedicated to it. So I'd probably propose deleting that. I don't know, Jack, have any strong feelings about that method?
Let's see. So there definitely is quite a lot of duplicated functionality in our existing disaggregation algorithms where they have to do a lot of messing around with metadata to save things to disk, and it feels like that should be abstracted out to the superclass in some way, but you're right that just taking a single chunk and writing that to disk is pretty much a one-liner, but there probably is some way that we need to help disaggregation authors to not have to worry about faffing around with metadata any more than they really have to. So specifically by metadata, I mean making sure that we write into the file that we're saving the correct names of the appliances and that sort of thing.
So this is
Jack,
basically for okay.
Sorry, I'm hearing quite a lot of like dropped words and sentences. Are other people getting what Jack's saying?
Oh, okay. I'm asking, is this basically for metadata, writing for metadata, right?
Well,
this method. I'm asking if this method is basically for writing the metadata.
So I think what Jack's saying was that it could probably do both.
Both, yeah. Okay, yeah.
I mean, yeah, as Jack said, like writing the data frame to disk is like a one-liner, but yeah, actually writing the metadata is pretty ugly at the moment, and I think we can all do better for that. But anyway, okay, I'll leave that for now. We can have a think about whether there's something that can be done there. Okay, so I just wanted to briefly talk through an example of this rather than just looking at the interface. So I'll see if I can run through the combinatorial optimization, which is a subclass of our. Well, in fact, it should be a subclass, but it doesn't appear to be at the moment. It should be a subclass of the disaggregator object. But I mean, you'll see that it does implement pretty much the same methods. Yeah, just because I think it's much easier to see an example rather than looking at the abstract definitions.
Yeah.
Okay, so kind of the internal model here is this this model attribute, which is a list of things that get stored later. So having a look at train, I think train doesn't quite fit our interface because it doesn't internally call a train on chunk method, but it does what you'd expect it to do. So it says for each meter, for each chunk. This is like a supervised training method. So we're expecting submeter data, So that's why we see individual meters in there for each chunk, and then this is doing the training for that chunk, and then it's storing what it's learned in this model list. So it's storing some states and storing some meters. But yeah, I mean, ideally, maybe we'd put this logic inside a train on chunk method if it was to, I guess, more closely match our interface. Having a quick look at import-export, if I remember rightly, this stuff never actually got imported to version 0.2 of NILMTK. I think this is just version 0.1 code. But I mean, you can see what it should be doing. It should be taking that model object, looping over some stuff, and saving it to disk, and then vice versa for import model. It should be taking what's on disk and updating the model attribute. Is that what you call Python class things? Attributes. So yeah, I don't think this would be that hard to add. And Jack, do you know why we're not using pickle here? Can we just pickle that entire model object?
Yeah, probably.
Actually, don't use pickle. It doesn't do large models. I've had tons of bad experience with pickle. I'm trying to remember what I used in mine.
Okay.
Where the heck is it?
Well, I mean, the aim here is that import and export are pretty general, right? So it's not like everyone has to store all of their models in a single model object. Like, store as much data as you want, and as long as you implement import and export, you can control how it gets written to disk, right?
Yeah.
But,
I think Nippon was keen to use JSON, so it's both easy for humans to read and easy for things that aren't Python to read.
Ah, nice.
So pickle is pretty. If you try and open a pickle file, it doesn't make any sense.
So basically, my experience has been really bad with pickle. I'm using JSON because I can have models that are 4 gigs in size saved.
Oh wow!
If you try to do that in pickle, it pukes.
Okay. So it might work for the CO model, but yeah, this is obviously if CO implements it, then it's kind of unique to CO. Any other disaggregation model can implement their own import and export, I think.
One other thing that might be worth highlighting in this file is, Ollie, if you can just scroll up to the top of this class. Yeah, so just under the declaration of the class, we have a docstring for the class. And the important bit about that is here we define what we're expecting to live inside the model attribute. And I would definitely encourage people to try and document this as well as they can and try as hard as possible to keep that documentation in sync with the code, because that just makes life so much easier when you're trying to understand what's going on. And obviously it's completely up to you what you actually put inside model, but
yeah, this is the important thing. Yeah, I haven't done this in my code. I think it's just this is very helpful for
but yeah, I agree that it's sometimes tricky to get around to, and goodness knows that a lot of NILMTK isn't documented very well, but it seems like these sort of documenting the data structures seems pretty important.
Yes.
Cool. Okay, so the last thing I wanted to show was the disaggregate.
One question about the data structures.
Oh, sorry, go on.
Yeah, so with mine, I actually have special Python classes to represent all the data structures, and they can be JSONized, no problem. So so I just thought I would bring that up. I don't know, because I don't just use like pandas. I just use that for the data set data. But actually, in terms of the the model itself, is actually a customized hash map.
Yeah,
cool.
so I'd imagine every algorithm would have its own like definition of what a model is, right? What representation of what it's learned, and I'm hoping that NILMTK isn't restricting anything here, and as you say, like serializing that to JSON is probably a really good idea because it's actually human readable, and potentially a lot quicker than pickling.
Python dict is actually a huge memory hog, so I had to write my own.
Nice. So this last function is the disaggregate function. As you'd expect, it loops over the chunks. I think then it calls disaggregate chunk on each of them, and finally it stores disaggregate chunk returns the results, and then it stores the disaggregation results to the data store. So again, it doesn't return anything; it just writes all the results to the data store.
So the results themselves, are they classification and estimation or regression results, or are they just one or the other, or can they be both?
That's a really good point. So at the moment, I think all we're writing are the regression results, as in the estimated power demand for each of the appliances. Which you're exactly right. That restricts what metrics we can calculate. We have a crude mapping between appliance power and appliance state within the metrics, but you're right. There's some lost information here, and I think we need to think more carefully about how to do this. If with the support states,
F-score you wouldn't be able to really calculate F-score properly without knowing how the algorithm classified, if it did in fact classify.
Yeah, exactly. So at the moment, the only state-related metrics we have are, I think, binary state-related metrics, which I think it's reasonable to convert the power to binary states. But as you say, like if you had multiple states, then you've already lost the information at this point. Yeah. So that's a really good point, and I'm not sure how we'd go about doing that in the future. But
I think we should implement, or I should implement the F-score that I came up with for multi-state appliances.
Yeah.
Because then we can truly test or come up with a metric that can represent multi-state appliances, not just on-off.
Yeah, I agree. We definitely should do that. But even before that, then we need to have a way of storing these states to the HDF5 structure, which I don't think we have at the moment. Jack, is that right?
I think that's correct. I think we have talked about it a long time ago, but I don't think we've actually written any code to do that. So are we just after basically another column, which is just state, and then some numerical representation of which discrete state the machine's in?
I think so. Although it's going to get tricky on the metric side, because it's like what would state 1 mean, what would state 2 mean. So okay, we need to think carefully about this. I don't think there's an easy solution. But that's a really good point. Okay, I'm going to try and add that to the list of things to discuss. So that's saving states to HDF. Yeah. Okay, so the last thing I wanted to talk about just briefly, I'm already overrunning, is the metadata, right? So not only do you need to save the disaggregated information to the HDF5 file, you also need to save the metadata. So what we do here is we define CO as being a meter device, which represents the appliances we've disaggregated, and then the mains device, which just allows us to copy over the mains data. So this is basically the input, and this is the output of our disaggregation algorithm. Then this is actually saving the meter metadata, so it's saying it's of type mains, as we specified above. Then what we do is we loop through each of the appliances and I think save them, or not save them. We're kind of adding them to this metadata structure. Where are we? I think we have device model of type CO, right? So this is a disaggregated appliance. We add them all to this big building metadata object, and then finally say save the metadata to the output data store. So this is all really quite complex, and I don't think it's worth going into it in detail at the moment. But the key is that you need to save a bunch of metadata for each appliance, along with the disaggregated data itself. So
this is definitely stuff that we can abstract out and make life a lot easier for metadata writers. So a lot of this code that we're looking at right now has almost literally been copied and pasted into the existing disaggregator subclasses. And there are just tiny changes that you need to make for each disaggregation implementation. And this stuff is really ripe for taking and abstracting out. And in fact, yeah, looking at this code now, I feel so troubled by it. But I wrote it. All this metadata stuff is my horribleness. So maybe one day next week I should spend on abstracting this out and then doing that in the existing implementations, and then hopefully it should be like 1 line or 2 lines for new disaggregation algorithm authors to come along and just get it to do the right thing and stick the metadata into the HTF5 file.
So would that be like an API for the metadata, Jack? So you call a method rather than actually writing the metadata yourself?
Yeah, so I was imagining that this would be a method inside the disaggregator superclass that you wouldn't override in the subclasses. Instead, you just call it and say, do the right thing, please, thanks.
Cool. Okay. Yeah, we should probably move on at this point. So that's a rough overview of how do I cross this out? That's a rough overview of the current interface to NILMTK, and it's definitely not perfect at the moment, but hopefully we can use what we learn from your algorithms to shape the interface so that it's maybe more general. And Stephen raised a really good point about the states. It's exactly that sort of thing that we need to think about and see how we can hopefully make it suitably general in order that most algorithms can fit it. Okay, so moving on. So the next one, I put Mingjun's code next. So the reason for that was that Mingjun has made quite a lot of effort already to kind of move his code in a NILMTK direction. So I thought that was a good starting point. So I'm just going to open that up now. So Mingjun, I'm going to try and give my understanding of the code, and okay. Feel free to jump in at any point if you think I'm saying something that's wrong or if you know a better way of doing it. But I just wanted to... Go on.
Yeah, my code I just based on your the code. So I think the structure is very similar to the disaggregation in the NILMTK before. Yeah.
Cool. Yeah. So it's a really good starting point, definitely. Okay. So this is like, I think this is like the main wrapper for, it's like a script to start the whole process off. Let's have a look. And the first thing I think we come across, yeah, this is where the real work gets done, right? So you create your latent Bayesian melding object, and you call its train method. So if I just jump into where this train method actually is.
Here I'm not training actually. I trained a method using the hash data train the model, and then I save all the parameters in a file. I just input all those the results of the learned parameters from the file. Just it's not training actually.
Yeah, so this is more like importing the model. Would that be right?
Yes, that's right. Yes.
And I guess training would be kind of determining the model from the HES data. But this is a really nice example because this is unsupervised training, right? So we're learning from some houses, but we're going to disaggregate on other ones. And this is not really something that we've nailed yet in NILMTK in terms of the infrastructure. And yeah, hopefully this is going to be a good example to point us in the right direction. But yeah, so it's a really good point. Okay, so this would be more like import model. Okay, so let's go back to where we were. Okay, so this is basically imported the model. So now our latent Bayesian melding object has some training data already stored, and now you call disaggregate on the mains data and give it an output data store, which is awesome. This is exactly the NILMTK interface, right? So let's jump into
exactly.
Cool. Here's a disaggregate function. If I have a scroll down here, again, you're looping over the chunks, which is great. So we're doing hopefully lazy loading here and not going to run out of memory on large data sets. And then you call, let's have a look, chunk resample, disaggregate chunk. So you call disaggregate chunk on each of the chunks. Let's jump into the disaggregate chunk method. And here, this is where I guess the real work gets done. And you return a prediction object.
Yeah, but before that, there's a let me see.
So I can see this is like a
okay.
It's like an optimization.
Yeah, and then it goes to the disaggregate fixed precision. I think this function. Yeah, this method.
So all of this code, including whatever's in disaggregate fixed precision, I guess would live inside the disaggregate chunk method, right? So it's in the correct place.
So this method is inferring the appliances. So the next one is called estimate noise variance. So this will estimate the precision in the model. So it will do several loops over inferring the appliance and then inferring the precision. So doing some loops. So the main code is in the fixed precision.
Okay, but the output of when you've done enough iterations, then you end up with the result of the disaggregation, right?
Yeah. The other result in the prediction, yes.
So what's prediction here? Is prediction a custom object that you've defined, or is it something else?
Prediction is the reading of the appliance, the components, the component appliances. Is the appliance? Yeah.
So is what's the type of the object? Is it something you've defined? Is it like a Python primitive type, or is it like a pandas data frame?
I think I think you should probably it's better to go to the disaggregate fixed precision method. Yeah.
Sorry.
Right. Okay. Yeah, this is the main algorithm for the method using the Mosaic solver.
Yep.
Yeah.
So I can see this is setting up all the variables and the constraints via the Mosaic solver, right?
Yes, yes. Yeah. So these are all the setting the constraints for the model. Yeah.
Mingjun, are you still there?
Yeah, yeah.
Oh, okay.
Okay. So if you scroll down, okay.
Okay.
Objective
so
function. Yeah. Yeah. This is a solve. So this will solve the problem. So the prediction is done. Yeah, here the prediction is the what's this?
Can't see where the prediction object. Oh, it's a dictionary.
Yeah, dictionary. Yes, yes, right. Yeah.
Cool. Okay. So
I stored here the time is the optimization time spent on the algorithm. So you see here the inferred appliance energy is the inferred appliance.
Okay, and you also store a lot of kind of
a lot of things.
Disaggregation.
Yeah, this is yeah, it's not. I should write something to explain what's the error.
So I mean,
the meaning of this? Yeah.
Is this for debugging or is this necessary? Are these values used?
Yeah, for yeah, I think some are for debugging. Some is the results. You see the inferred appliance. There should be an inferred appliance.
Sorry, in here. Inferred appliance energy.
Yeah, this is the inferred appliance energy. Yes. Yeah, also retain the inferred number cycles. The cycles means how many times you use the appliance.
Yeah. So
yeah.
So I guess the question is whether you could fit the NILMTK interface and just return a pandas data frame of of just the power of that appliance. I mean, I've gone too far. Yeah. So disaggregate fixed precision. Yeah. Is called within disaggregate, right?
Yeah.
Disaggregate was in this file, wasn't it? Yeah. So I wonder whether disaggregate chunk could just return the
chunk. Okay.
Whether it could just return a pandas data frame, or whether it also needs to return all that metadata. Is there an elegant way of doing this, of like returning multiple objects in Python? How does Python? You can do that in Python, can't you?
Yeah.
Yeah. Okay. Yeah.
You mean like as a return type?
Yeah.
Yeah. Just make it a tuple. You can return as many arguments as you want.
Yeah.
So.
You mean write the result into a file?
No.
No.
So the current NILMTK interface is that the disaggregate chunk returns. That's trained on chunk. Scared me for a moment. Disaggregate chunk returns a pandas data frame object, right?
Yeah.
And it'd be great if we could make it such that all algorithms do this. But I'm wondering whether it really needs to, because disaggregate chunk is kind of internal to the algorithm, and probably disaggregate is maybe the only externally visible method. What are your thoughts, Jack?
So I'm increasingly thinking of these in-memory ones as being part of the public API, because definitely in my work I generally do stuff that just lives in memory when I'm sort of doing my research on disaggregation algorithms, and so everything I do is disaggregate on chunk, and it's just kind of at the very end when I want to test it on large amounts of data that I want to be able to handle multiple chunks. So
okay.
Yeah.
Yeah, I can understand. Yeah, if it is too large memories for very big data, then so chunk is helpful. Yeah, is that?
That's right. Yeah.
Yeah. So okay, let's leave this for now. But I guess we just need to put some thought into how we could deal with the additional metadata in addition to fitting the NILMTK interface of returning a pandas data frame from disaggregate on chunk. But anyway, as I say, let's leave this for now and move on. I think this pretty much covers everything in. I guess let's go back to the disaggregate function, because I think Mingjun, you started to look towards the metadata, but I don't think. Yeah, so you call disaggregate chunk, and there's a load of commented code down here around storing metadata.
Yeah. I tried to using the metadata, but it always there's always error. So,
there's always an error. For me as well.
So I just stopped just working on the code. Then I just left it. I should do this later. Yeah.
Yeah, well, I think we should work with you on this because it's complicated.
So just to emphasize again. My proposal. So my proposal is that you shouldn't have to do this. My proposal is that all of this will go away, and you'll just have a single line or two lines maybe that you need to call, because like you say, this is all a bit messy, and actually the changes between different disaggregation algorithms are sort of a fraction of a percent to this code. So next week I will modify the disaggregate superclass so it has a method which does all this for you, and then I'll implement that in the combinatorial optimization and factorial hidden Markov model subclasses so you can see how it works, and maybe even if I have time I'll write a bit more documentation on this. But you're absolutely right that this is a horrible mess, writing the metadata like this, and all of this should be abstracted out.
Cool. Okay, one last question I wanted to ask Mingjun before we moved on. So Mingjun's code is really interesting because it's an example of an unsupervised algorithm, right? So he's learning a model from some Hess data and then potentially applying it to maybe other homes in the Hess data or maybe homes in another UK data set. So how did you go about this, Mingjun?
So here I'm using the Hess data for training the parameters in the model. I then apply the model to the UK dial. That's Jack's data. Yeah, it's applied to that. Yeah.
So Mingjun, did you have to specify which meters are, or rather which appliances are in the UK dial house?
So there in the Hess data there are a lot of appliance data, a lot of readings for appliances. So I assume that for the prediction, I just assume that I have known which appliances you're using. So then I just select the appliances from the Hess data to make prediction in the new house. Yeah. If you go to the demo LBM, so I first, so you see the appliance, the meter list.
Sorry. Yeah.
So these are the appliances I want to predict from the UK dial. This is the building 2.
Cool.
Yeah.
Oh man, hopefully using NILMTK metadata, all of this appliance map should go away. But okay, so this is the equivalent of doing an appliance survey in the house you want to do disaggregation in. You don't need to know any parameters about them. You just need to know what types of appliances are in this house.
Yeah. So I need to. So I assume that if I have known which meter, which appliances you want to predict.
Cool. Okay. Yeah. We should also think about how to include this in the interface. But cool. Okay, that's really good. I think that mostly covers everything we wanted to here. Should we move on from this code onto Stephen's code and discuss that? So we have 20 minutes left. I think, Jack, you have to run at 5:30. Is that right?
Ideally, like. The
sky's
not going to fall in if I don't make it.
let's try and keep it to an hour long anyway. That's what we allocated. Okay, so Stephen, again, I'm going to have a go at explaining your code, and you can tell me whether I'm massively wrong.
But before you do it, I just preface it a bit. So I think my architecture is quite a bit different than NILMTK in that I'm providing a training an environment outside of the implementation of an algorithm, and that just an algorithm and a data gets specified, but we can talk about that later on. So there is a bit of a difference, but we'll go over it later.
Okay, cool. But I mean, I like the separation already. So this script seems to be an example of training and saving to disk, and then the next script is an example of taking what you've learned from disk and then using it to do some disaggregation, I think. Is that right?
Yes.
Cool. Okay, so let's have a look how this works. So so is this SuperState HMM the object that contains?
Oh, you kind of
is that the case, Stephen?
Oh, sorry, you kind of faded out there for a second. But it basically contains the model, all the model data.
Stephen, are you still with us? I can't hear you if you're saying anything.
Yeah, I'm here. Can you hear me?
I hear you now. Sorry, I think my audio is dropping out. I wonder whether it's showing the screen.
I can see the screen.
Yeah.
Maybe
I can hear you both.
Can you turn your video off? That might be causing some bandwidth problems.
Yeah, sorry, you keep dropping in and out, and I can't hear you. I think it's me sharing my screen. I don't really know how to reduce the bandwidth.
But I think Mingjun needs to turn the video off because it's probably eating up some bandwidth.
So I should turn off the video, okay?
Yeah.
Yeah. How to turn it?
I mean, you sounded all right there, Stephen.
Okay.
Yeah. Do you want to go?
Okay. So yeah, the SuperState HMM that holds all the data for the model.
Okay, cool. So it's a case of like serializing this to you use learning over the data.
Yeah, I do that at the bottom. JSON dump.
Cool. Okay. So basically, all of this stuff, I guess, would go into the export model. Is that right?
Yeah, you could. That was basically for me creating graphs and stuff like that, and just basic reporting.
All right. Or is this the code that does it? Is that printing to the screen or something? Yeah. Okay. So this JSON dump is clearly like the export model function, and then up here would go into the train function, right?
Yeah. And depending on the folds, right? So if you're doing 10-fold cross-validation, there'll be 10 models created.
Okay, we need to think about this. So are you looking at supervised disaggregation here, Stephen, right? So if you have 10 folds for testing, then you're going to learn 10 models, right?
Yeah.
Okay, so I wonder whether, so in NILMTK, I think we've always put this folding outside of the disaggregation. This would be outside of the disaggregation algorithm. So the algorithm would take care of like, here's some data, learn a model for it, and I guess you'd end up with a different disaggregator for each fold of the data. Does that sound right, Jack? Is that the right architecture?
Yeah.
Cool. Okay, so this folding stuff, I guess, would be outside of the algorithm, but obviously everything inside it would be inside the train method. Does that make sense, Stephen?
Yes, that does. Yeah.
Cool. Okay. Let's move on to the algorithm section. Right. So I guess this starts with loading it from disk. Loading the model from disk somewhere.
Yeah. So first of all, you have to specify what algorithm you want to use. So for instance, you have the alg_viterbi. So you would specify the algorithm and the algorithm name as part of the parameter.
Okay. So that could be passed as an optional argument to the disaggregate function, right? The disaggregate method of the disaggregator.
I mean, it doesn't have to be that way. My whole idea was that because I have two algorithms, Viterbi and sparse Viterbi, I wanted to use the same testing for each algorithm. I thought it would be nice just to specify the name as part of the.
Okay. Yeah. I mean, I think every disaggregation algorithm will have additional parameters that you can pass it. I don't know whether we should have like comma, whatever it is.
Yeah, so this is why I say it's kind of reverse, right? Because test algorithm is my agent for testing, right? And so and basically you tell it what algorithm to use, and it will go call that algorithm and store the results and process the matrix for accuracy.
Yeah. So in NILMTK, we don't really have a separation between models and algorithms, right? So here your underlying model is a type of HMM, but you have two inference algorithms that you could run over that model, right?
Yeah.
So I don't know how that would work in NILMTK. I don't know whether you'd have two disaggregators. I wonder whether you just have one disaggregator, but then just pass it as an optional argument, because it seems to be it's only specific to the disaggregation, right? It's not specific to the training or the model. So yeah, I guess
the idea was you can actually reuse the model. Like, so if I decided to implement bomb Welsh, I wouldn't need to rewrite all the SuperState hidden Markov model stuff. So I can easily do something where I have a base class called sparse HTM or sparse NILM, and then from there I can inherit that to different algorithms that I create, basically, if I want to. And yeah, within sparse NILM would be the training part. So instead of having a separate file called train SuperState hidden Markov model, that would be part of the base or the superclass or a class in between called sparse NILM.
Yeah, so I mean, I think your whole disaggregator would be called sparse NILM, right? That would include the disaggregation, so the training that we've just described in the other file. But then you'd have a disaggregate method that you could pass an optional argument, just like here. I think we have an optional argument of sample period. Yeah, so we get off the sample period, and you could equally pass in Viterbi or sparse Viterbi, or I can't remember what the options are, but that makes sense, right? So we still follow the same interface, but you can just I guess you'd have a default inference algorithm, and then you can optionally specify a different one if you want to.
Yeah, that would be no problem. That's the way I had it before I rewrote stuff. So.
Oh man, I'm sorry. No. I'm just trying to get this mapping right between what exists and what we can support.
No, it's no big deal. I mean, it's very simple changes. These are not like huge architecture things, right? So it's just cutting and pasting code basically in different spots.
Yeah, so I guess so disag algo is what you decide. Oh yeah, here we go. I opened it earlier. Right, so here's your
every file that has algo underscore has this common function. So if you were to load up the algo underscore sparse Viterbi, you would see the same thing, basically.
Cool. I mean, so yeah, you would just, I guess, have them as private functions within your disaggregator, and then your disaggregate method would decide which one to call. Yeah, I guess we'd have to give some thought about how to nicely chunk that stuff. But I guess chunking works by the chunk should be as large as you can possibly fit into memory, right? It's not going to do chunking unnecessarily. So you can expect each chunk to be large and hopefully cover enough data for your HMM to be worth it.
Yeah, I mean, ideally, I just like for each algorithm, it only cares about the past reading and the current reading. It doesn't care about anything else at any point in time.
Yeah.
And that's why you see just the Y0 and Y1. Yeah.
But hang on, I'm confused. But the Viterbi algorithm requires a whole sequence of power demands, right?
Not if it's online Viterbi. If it's online Viterbi, then it's more like you're doing more like a Markov style thing where you're at any point you're just looking at the current and the past reading.
Yeah.
So, okay, I see what you mean here. So, but I mean, I feel like this isn't exact inference, right? Because later on you could run your Viterbi algorithm over a larger sequence and get a different result.
Yes, you could. Yeah.
Okay, so yeah, obviously you can specify the size of your window, right? How far back you want to go, whether it's just one sample, which I guess is the least computation you could do if you need to run it on a low power device that doesn't have many cycles. But if you're running on a supercomputer, clearly you can have a longer window here.
Yeah.
Cool. Okay. So then I guess there's one other thing that I think I noticed earlier. So I think you do accuracy calculation within this loop, right?
Yeah. So the accuracy calculation is about 9 lines down.
Mm-hmm.
Oh, you went really far now.
Oh, sorry.
From where you were. Yeah. So you see. Okay. So at the top it says detangle, right? And so I'm getting the states. I'm making estimates. Blah blah blah, and then there's ACK classification results, ACK measurement results. So, so those 2 lines is where I do the calculation of the accuracy.
Yeah. Okay. So clearly, I mean, we'd love to have these as metrics in NILMTK, but in order to do so, we need to think about how to store the states to disk, right? The estimated appliance states to disk as well as the appliance powers. But yeah, I mean, if we solve that problem, I don't really see a reason why this wouldn't work, right? So functionally, everything seems to kind of fit. I mean, we're all doing the same things here, right? We just have a very different way of structuring the code. But okay, that seems pretty realistic. Is there anything else you wanted to mention, Stephen, before we move on? I think it'd be good to kind of just list all the things that we discussed that we need to solve, I guess, to move forward with this. Is there anything else we should discuss with this algorithm, or anything you think might not fit the NILMTK interface?
No, I think we discussed everything.
Okay. All right. Let's cross that out, and all right. Let's move on to the things that are left. So just before we do some random questions, let's have a quick look at some actions. So I gave myself an action, which was write how to write a disaggregation algorithm docs function, which so docs page, which doesn't. I mean, it's listed in the contents page, but there's no link underneath it. So I think we can do more to help other people write NILMTK disaggregation algorithms rather than just looking at the examples that exist. Obviously, I guess that would change. So Jack, do you think it's realistic that you'll find time to do that metadata API that you mentioned? I mean, you're in writing mode, aren't you?
Yeah, so that means I'm enthusiastic to find ways to procrastinate writing my thesis.
All right, well, so, yeah, I'll write it. It's up to you whether you do it or not.
Yeah, so at the moment I've put into my to-do list that sometime next week I will try and find a day to do this. So, Ollie, what I'd propose is maybe if you can hold off writing the docs until I've done this, because that should make life a lot easier for both writing the docs and for people writing new algorithms. So yeah.
Cool. Okay. So that's pretty clear. So the thing that we just stumbled across with Stephen's algorithm is that I think we do need to have a way of writing states to decide how to write states to
just looking at the metadata schema. So we might already have a way, which is you say physical quantity equals state, and then you use an integer to refer to the specific state. So the column heading would kind of be physical quantity equals state, sort of thing.
Awesome. So you've already thought of this, Jack.
So I think we did bounce some of these ideas around long ago, but NILMTK doesn't know what to do with state yet. So I think basically we've thought about it in the metadata schema, but NILMTK I don't think has any code to handle this yet. So we're kind of part of the way there, but and if anyone can think of a more elegant way of including this, then that would be a good thing. So Stephen, do you at any stage assign human readable identifiers to each state, like spin cycle and heating water cycle and that sort of thing? I assume not.
No, it's all algorithmically determined in foreground truth. Yeah.
Okay.
Cool. What else did we come across during this conversation? I guess there are clear actions for Mingjun and Stephen, if you're up for it, to look at making these changes to bring the algorithm interfaces in line with NILMTK. I guess a question which we should probably discuss now is where would you guys like your code to be hosted? Would you prefer it was part of the NILMTK repository, or would you prefer it was part of your own repository and just marked as NILMTK compatible? Do you have strong feelings?
For me, personally, I think it needs to be in both. One would be what I would call testable versions, and the other one, it would be current research, basically, that may not be suitable for being in NILMTK at that moment.
Yeah.
Okay, so you'd keep your own repository for your own research, but then you'd periodically try and put stuff in NILMTK repository in terms of
because
stuff that other people can reuse.
Yeah, so what I might want to do, right, is I might say, okay, I have sparse Viterbi and I'm satisfied with that. So the next, instead of changing sparse Viterbi, I'll actually create a new disaggregator.
Mm-hmm.
Oh yeah,
So,
yeah.
okay.
Mingjun, what about you?
So I use the NILMTK in my local computer to write those codes. Then, but now I don't know how to submit my method to the NILMTK that someone else can use it. That's
Okay, so I think if you're keen to contribute the code to NILMTK, then that's great. And I think the right way of doing that is through Git's pull request system. There's lots of documentation online for that, and we can help you out with that. But I think maybe Jack can correct me if I'm wrong. But I think what you would effectively do is you would branch the NILMTK repository and make changes on your local branch. You would commit all those changes and then submit a pull request, which we would then see. NILMTK would see all of the changes that you've made, all the code you've added, and then we'd be able to comment on that pull request or accept it to sump all of that code into the NILMTK main repository.
okay.
Jack, is that roughly right?
So there's a form way to commit my or to push my code to the NILMTK.
Yes, yeah, exactly.
In a branch, yeah. Okay. So
the last link that I copied into our group chat is.
So I haven't used this. I will learn how to use this to push my code. I think, yeah.
Fork the repository, not the branch the repository. Yeah, this is new to me as well, Mingjun. So, but Jack knows a lot about this, right?
So can you see the links that I've pasted into the group chat on the Hangout window? So just to the right of Olive's screen, is there some text that I've copied into there?
You need to press the blue chat button in the top left. I'm just highlighting it on my screen. It's probably somewhat visible to you.
Wow, okay. Yeah.
So that should show and hide the chat. But anyway, I'm going
to... but yeah, we've got some documentation on how to do this specifically for NILMTK.
Yeah, I will learn this, how to do... So I think I will write my code in my local computer and then push it to the so here the GitHub. So that's what I should do. Yeah.
Yeah.
That sounds good. So there's an alternative which we've been talking about. So there are kind of two fundamentally different sort of approaches for doing this. One is that we try and have NILMTK as this central repository where the universe of disaggregation researchers commit their disaggregation algorithm, and then that means that for users, they don't have to worry about installing any new software. They just install NILMTK, and then magically they get everyone's disaggregation algorithms. An alternative is that NILMTK just hosts these kind of benchmark algorithms, and then for these cutting-edge algorithms, they would live on your own private, not private, but your own repository on, say, GitHub. And so if people wanted to use your code, they would first install NILMTK, and then they would install your code, and your code would hopefully sort of call NILMTK and that sort of thing, but ultimately your code would live on your own repository, and that means that you would have total ownership over it. If there are bugs, then you can fix them very quickly and very directly, and it also means that sort of bug reports for NILMTK are specific to the kind of NILMTK core, rather than algorithms which are written by people that we might not be in direct contact with. So these are kind of two different ways of publishing cutting-edge algorithms, and certainly Ollie and I have talked about it, and I don't think we came to any particularly solid conclusions. Is that right, Ollie? Or we kind of...
Yeah, I mean, I'm really conflicted about this.
So another thing is, so my method is using the Mosaic solver, which will be, so we have to additionally apply for a key for the Mosaic solver. So
yeah, I think that's absolutely fine. I think as long as there's some documentation, at least in the doc string of the disaggregator class, then that's absolutely fine. I mean, if it did end up that your code was in a separate repository, then you can easily put in a README file to show your installation instructions. But
yeah,
I guess it kind of depends where it's hosted. But yeah, as you say, Mingjun, I think dependencies on external libraries is inevitable, and I mean we should totally expect that as algorithms get more complex, and it's absolutely fine.
Yeah.
Yeah, absolutely. And I think that for me maybe makes me lean slightly towards the idea of hosting this somewhere that it isn't the NILMTK core repository, so that we don't have this kind of ballooning set of dependencies just to install NILMTK. But I'm not entirely. I'm happy to be persuaded otherwise, and we can discuss this in more depth.
So I agree, Jack. That's difficult. Do you think it makes it harder for users to use disaggregation algorithms that aren't in the main NILMTK repository? Or, I mean, how would we, as long as we list it and make it easy for them to find, it should be okay, right?
Yeah, exactly. And one thing that we're not doing at all well at the moment is using all the automated mechanisms for installing all the dependencies. So at the moment for NILMTK, it should, instead of having that long installation documentation, all of that should be in one machine readable file. So you can just do sort of pip install NILMTK, and magically all the dependencies will be installed for you. And then when you come to install someone else's disaggregator, then hopefully they follow the same convention, and the user would just have to do pip install amazing disaggregator, and it would install the dependencies. By the way, I don't think this is necessarily very hard for us to do, and we're getting near to doing it. Like it's probably like 3 hours work or something, but it's just about trying to find those 3 hours.
Cool. All right. I guess that brings us to the last point. Is there any other business? There's no one else on the call, is there? That's not any of us talking. No. Are there any other things you wanted to bring up that we haven't discussed so far before we end the call?
I think I'm okay.
Okay. Yeah, everything's fine. Yeah.
Cool. Okay. And let me just put a last point down to discuss dependency management, I guess.
Yeah, and where to host cutting edge algorithms.
Yeah, so for mine, there shouldn't be any dependency problems. I don't like to tend to use a lot of different libraries, so. The only catch is I was using Python 3, so I don't know if.
Oh yes, that probably is something we'll need to look at. I don't think we've explicitly tested NILMTK on Python 3, which is to say we haven't tested it on Python 3. I think we've tried to be careful to make sure that it should work on both 2.7 and 3, but we haven't tested it on 3 yet.
Yeah, hopefully it wouldn't be too hard to make just standard Python 3 codes work on Python 2.7 though. I don't know. Maybe I'm getting quite bold here.
You just run into like the print statement problems and things like that.
That's the worst problem, isn't it? That's the only difference. Cool.
So maybe one other very quick thing to mention is, so as Ollie mentioned, I'm currently writing up my thesis. But then as soon as that's done, I've got 3 months of postdoc at Imperial, and one of the aims of that bit of work will be trying to compare different algorithms, which is to say that I should be able to justify spending a reasonable chunk of time helping you guys get your code into a state where we can run it in NILMTK. So that will be sort of sometime after January next year that I should have a little bit of time to help, hopefully.
Cool. It's pretty exciting. Cool. All right. Well, I think that's covered just about everything. Thanks so much, guys, for joining us. I think it's been a really good call, and I think we're well on our way to getting these algorithms NILMTK compatible. Even as Jack said, even if they don't end up in the main NILMTK repository. But yeah, I think it's a real step towards reproducible research in NILM, which let's face it, has been pretty tough so far.
Yeah. Well, thanks for organizing this and hosting it. Both
no problem.
Ollie and Jack, it's really appreciated.
Ollie did all the work organising this, so yes, thank you very much, Ollie.
Thank you. Yes.
Yeah. No worries. All I did was email you guys. Cool. Okay. All right. I'll end the broadcast now, and yeah, hopefully we'll have some good results soon. Cheers, guys.